recognize. This notation is due to SID-bond. So you see all this labeling, and you now understand what it means, right? So this is for krypton, very simply for krypton. They are labeling. There's also three letter, right? Three letter. You have all this L, M, and so forth. Okay, so it's the same idea. Just a labeling system that you got. Okay. So much for XF. Now you can do a angle resolved photo emission equivalent of XF. It's called angle resolved photo emission extended fine structure, and this eventually evolved into photoelectron holography. A very exciting field for a while, and then it become a little bit, it's fizzled away because the analysis of the holography, or hologram, so-called hologram, becomes so complicated is that people lost interest. Essentially, the material chemists lost interest because it just takes so much work to generate some 3D structure. And it's very nice because you can do the calculation and calculate, because you do a complete 3D image of your material, complete modeling material. But it's very tricky for people without a strong physics background to do this kind of work. But what it is very simple, is that in the case of XF, right, in the case of XF, you measure everything. You measure the emission from all directions. In the case of RPAPS, angle resolved photoelectron fine structure, you select the direction. Okay, so you measure the angular distribution of that emission instead of measuring, averaging all the time. So it pro-directional interference modulation to give you, so for example, here is a classic example that photon comes in and it ionizes a 1s orbital, right? So think of it as sulfur atom and sulfur on nickel. That's the first experiment that was done on using RPAPS like this. And the emitted wave is so-called, because you have to have a dipole transition. So the outgoing wave must be a P wave, because you have to, photon has angular momentum of 1, so therefore the outgoing wave is a P wave. It looks like this. The P wave hit the nickel atom, right? So sulfur is absorbed on top of the nickel surface like this. So this is my sulfur atom, and then you have a nickel surface. And hit this, and then it eventually emit, just like you remember the electron scattering curve that I showed you earlier. It's just like the electron scattering off your lattice. So here you have a P wave scattering off your nickel surface, and you have these sort of scattering intensity, electron scattering intensity. And so what it does is that you have some computer program that measure the backscatter cross section. Essentially, you consider scattering off each of these atoms, 1, 2, 3, 4, right? All the neighbors from the sulfur atom, and then you sum up your intensity. Okay, so it's a hard work. It's kind of a tough work to do, because you have to measure your photoelectrons. From each of these photoelectron intensity, you build your curve. So you build your kinetic energy curve, and you generate an exact curve like this, right? Similar to what you have in a certain direction, right? You focus on one particular direction, and you do the same thing. Essentially, you then from that direction, you then do the Fourier transform. You got RPAPS, for example, sulfur and nickel atom, sulfur and copper atom, compare with XF, right? Sulfur and nickel using XF technique, and you got these curves. And in the case of angle resolved fine structure, the intensity here is stronger. The intensity is typically 5 to 10%, whereas compared to XF, it's weaker. It's 1 to 5%. Okay, so for doing angle resolved for emissions has some advantage in terms of signal to noise that you can get better. And you can go through the same, if you want quantitative analysis, you can go through the same process of analyzing this. You can scaling theory. And so here you have a chi-curve, right? You have filter data, so the chi-curve, and then you assume the geometry of your material, right? So you assume a structure here, you generate a physical structure, and then from this structure, you generate your chi-curve, which is your the solid line that you see, and then you compare, just like LEED, you compare how well do they agree, and then you can vary one of the parameter of your structure, and then generate another curve and compare again, and from there you can calculate the R factor, just like the LEED that you calculate, and then you can tell which one give you the closest one. Okay, so I'm almost done with this, and so I'll stop here, and next day we'll finish by talking about STM.